Okay, so hello and welcome everyone to the third week of interactive live sessions for Fundamentals of Convective Heat Transfer. This course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of IIT Guwahati. I'm Debjit. I'm a PhD scholar at IIT Madras, and like every other week, we shall be solving some problems together. So let's get started with problem number one, which is asking us that for boundary layer flow over a wedge, if the wedge angle is negative, the flow accelerates along the surface. Is that statement true or is it false? So given I have a plate like this, a pair of plates like this, which are parallel to each other, and then I have a wedge with a negative angle, meaning like this. Sorry. So in that case, will the flow accelerate or will it decelerate? This being the angle, which is usually represented by beta, and this beta we'll assume is the same for both the wedges. So if we take a look at the solution, this is actually false because it does not accelerate, it rather decelerates. So if we go back here, we can see that the area of flow is increasing. So it makes sense that the velocity of flow would get reduced. It will slow down. So it does not accelerate, rather it decelerates. Now, if the wedge angle was positive, meaning it went from something like this to something like this, which you can see in cases of nozzles, then the flow is accelerated. Draw this a bit better. Yeah. So this is the case of a positive beta or wedge angle. So in this case, it accelerates when the wedge angle is positive. Okay, so moving on to question number two. This is asking us whether Kohlberg analogy relates what? So does it relate? Option A, fluid friction and pressure drop. Option B, fluid friction and heat transfer. Option C, heat transfer and mass transfer. Or is it option D, none of the above? So what does Kohlberg analogy tells us? There are four options. Read the question and the options carefully and then try to pick the correct answer. So we'll now take a look at the correct answer. It's actually option B, that is fluid friction and heat transfer. So the Stanton number at X is basically the Nusselt number divided by the Prandtl number and Reynolds number. So, and Kohlberg analogy tells us that this is equal to 0.332 Reynolds number to the power, it's 1/3 minus 1, so minus 2/3, and Prandtl number 1/3 minus 1. So that's sorry, this was half, and this is 2/3. And as it turns out, so if I write it this way, this into Prandtl number to the power 2/3, this is equal to 0.332 divided by RE power half, which happens to be equal to the coefficient of friction at X. So this is precisely what Kohlberg analogy is. So given you know the friction factor, you can find out parameters related to the heat transfer from it. So this basically a combination of Stanton number and Prandtl number. If we know the Prandtl number, then we can always go back to the Nusselt number, which gives us information about the heat transfer, because we know that Nusselt number is the non-dimensional uh, convective heat transfer gradient. So Nusselt number equal to HL by K, or in this case Hx by K, since these are all local values. Okay. Cool. So this is what pole one analogy is. And another special case of it is when Prandtl number is equal to 1, then this equation, this gets simplified to Stanton number being exactly equal to the friction coefficient. Uh, this is known as Reynolds analogy. This is for Prandtl number equal to 1 only, and for any Prandtl number we have this, which is known as the Colburn analogy. So it connects fluid friction to the heat transfer. Right. Okay. So moving on to question number 3, which is asking us for the expression of local shear stress tau W at the surface of a flat plate. For the Blasius equation, you have to consider Blasius equation, and primes denote the differentiation with respect to eta. That is just something we use, but it's mentioned here. So you see these f double primes, that just means f being differentiated with respect to eta twice. So I'll just explicitly write this. F double prime simply means dou 2f dou eta 2. Sorry, uh, dou eta 2. That's all. So let's take a look at the solution. It's actually option C. So how do we get there? So first of all, we have to start with the Blasius equation. So a few things which we need. So first of all, we need the tau W, which is tau or shear stress at y equal to 0. So this is basically mu, the uh, coefficient of viscosity, multiplied by the gradient of velocity at y equal to 0. So this dou u dou y now can be written in a different way. We can write this as dou u dou eta multiplied by dou eta by dou y. And we know that in the Blasius solution we write that u by u infinity is equal to some function f prime, which is equal to y by, sorry, which is a function of eta, and eta itself is y by under root of u infinity x by mu. Right? Did I do this correctly? This is Reynolds number, right? So this does not seem correct. This is meter per second, meter square per second by mu x. Sorry. Let's just check the dimensions quickly. The other way around. Mu x. Yeah. So now, okay, so from here I can tell that dou eta dou y is simply 1 over this thing, mu x by u infinity, and dou u dou y, from here I can simply write u equal to f prime into u infinity, and f prime is basically a function of eta. So if I take one derivative with respect to eta, that is dou u dou eta, this simply gives me f double prime, and u infinity is a constant. So we will now simply plug in these values here. So mu into dou u dou eta is u infinity into f double prime, and dou eta by dou y, we'll write this way, u infinity by nu into x. So this matches with our option C right over here. So these two are same. Okay. So now moving on to question number 4. This is a numerical type question. It's asking us that a 2.2 centimeter outer diameter pipe is to span across a river at 30-meter wide section while being completely immersed in water. So what we have is a river flowing, and in between we have a circular cylindrical pipe like this with a length of 30 meters, and the diameter is 2.2 centimeters. So in meter I will write 0.022 meters. That's the diameter of it. Now there is a flow through the river, so the average flow velocity of the river is 4 meters per second. So I have a u infinity coming in at 4 meters per second, and the water temperature is 15 degrees Celsius. That's also given. So T ambient is 15 degrees Celsius, T infinity. Sorry. Determine the drag force in newtons exerted on the pipe given the density and dynamic viscosity of water at 15 degrees Celsius is this one. So rho is 999.1 and mu is 1.138 into 10 power minus 3, and the drag coefficient is also given, CD, which is equal to 1. So basically there is a drag force acting on this. We have to find out how much is that. So the way to do this is, we have to first start with the CD. So coefficient of drag, as we know, is basically the drag force divided by, so the drag force is then normalized by the stagnation pressure, which is rho u infinity square by 2 multiplied by the projected area of any body. So this is a bluff body which is projected. So if I now look from this direction, the direction where the flow is coming in, I would simply view this cylinder as a rectangle. That would be the projected area, right? So this being the length and this dimension being the diameter phi. So I know these values. So this shaded area is the AP that is considered here. So from here we will write down FD is equal to half rho u infinity square AP into CD. So now we'll just plug values over here. So it's half into density rho is 999.1 multiplied by u infinity square, which is 4 squared, and then the projected area, which is length into diameter. So we know those values as well. 30 multiplied by 2.2 centimeters, which is 0.0022 meters, and the coefficient of drag, which is simply 1. So we can now do this calculation. In a moment, I'll do this calculation. So that's 999.1 multiplied by 4 square, which is 16, into 30 into 0.0022, and this whole thing divided by 2. So that brings us to a force of around 527. So the drag force is 527.5 newtons. So that's the total drag force on this cylinder. And this is how you calculate it. Alright, so simple question. We'll keep moving on. We'll move on to question number 5 now, which is asking us the ratio of kinetic energy of flow to the boundary layer enthalpy difference is called what? Is it option A, Stanton number, option B, Jacob number, option C, Onazorga number, or is it option D, Eckert number? So these are all dimensionless groups which are frequently used in fluid mechanics and heat transfer and allied fields. So among these, which one represents this particular ratio, the ratio of kinetic energy of the flow to the boundary layer enthalpy difference? And the correct answer is option D, Eckert number. So we have come across this number earlier. So Eckert number, we found it as U infinity squared divided by Cp into T wall minus T infinity. So this basically represents the enthalpy difference, and this U square represents the kinetic energy of the numerator. Right. Okay. So simple question. Moving on. This is again a true or false type of question, which is the statement is that the average Nusselt number, which is sometimes represented by nu bar or nu bar, over the entire plate in case of a laminar flow. So there is a flat plate and there is a boundary layer and a laminar boundary layer. And we are telling that the average Nusselt number over the entire plate in case of laminar flow is twice the value of the local Nusselt number at the end to the plate. So if we are considering a plate of length L, then all I'm saying is that this Nu at L, the local Nusselt number, is, so the average is twice. So the average is twice this. So mathematically, this is what the statement is. Now, is that statement true or is it false? Let's take a look at the solution. It's actually true. So the local variation of Nusselt number, if we look at that, so let's say this is L, and sorry, and if this is Nusselt number local, then we will find something like this, or NUL. Then we will find its variation something like this. Draw this properly. It's a hyperbolic type shape. And as it turns out, the average of it goes something like this. This is the Nusselt number average, and this is the Nusselt number local at the end of the plate. And this is exactly double of that. So the average Nusselt number is equal to twice the local Nusselt number. Right. So the expressions for them are like that as well. So this is 0.332 into Prandtl number power 1/3 Reynolds number power half, whereas the average one, that is 0.664 into Prandtl number to the power 1/3 and Reynolds power 1/2. So Reynolds power half. So the average is twice the local value. And as a result, this statement is also true. Alright, so moving on, we'll move on to question number 7. This is asking us, this question has given us a velocity profile, which is this, that is u by u infinity is equal to twice of y over delta minus y over delta whole squared. So you have to now find the ratio of delta star over delta, where delta star is the displacement thickness and delta is the boundary layer thickness. Okay, so if we take a look at the solution, it's 1/3. And how do we find that? So first of all, we need to find delta star and delta individually. So let's start with delta star. We know that the displacement thickness can be measured like this. So 0 to delta 1 minus u over u infinity into dy So if we now replace u over u infinity by the profile that we know, so we'll get 1 minus twice of y over delta, and minus two minuses cancel each other out and gives us plus y over delta whole squared, and this thing integrated with dy from 0 to delta. I'm coming here. So if we now actually perform the integration, the first term gives us delta, the second term gives us 2 over delta, then y integrated once gives us y squared by 2, and that going from 0 to delta would give us delta squared by 2. And the last term, we have 1 minus delta squared outside, and y square integrated, it gives us y cube over 3, and from 0 to delta that would simply be delta cube over 3. Now these 2's cancel out, and what we are left with, and okay, so this delta cancels out with 1 delta, this delta squared cancels out 2 and leaves us with delta only. So if we take delta common, we are left with 1 minus 1 plus 1/3. So 1 and 1 cancel out and we have delta over 3. So it's basically delta star equal to delta by 3. If we take the ratio delta star by delta, we get 1 over 3. So, and that corresponds to option number 1, that is 1 over 3. That's how we get this ratio delta star by delta for the given velocity profile. Alright, so moving on, we'll move on to question number 8, which is once again a true or false type of question that is asking us that higher the value of the shape factor, the stronger is the adverse pressure gradient. So the shape factor is defined as follows: H is equal to delta star over theta. Now delta star is basically the displacement thickness, which we saw in the earlier question, and theta is the momentum thickness, and the ratio of them is known as the shape factor of a boundary layer. Now given this statement, is it true or is it false? Let's take a look at the solution. As it turns out, the statement is true. So given there is an adverse pressure gradient, what happens is that the boundary layer actually thickens, and this thickening leads to a rise in delta star, that is the displacement thickness. The momentum thickness also rises, but not as much as the displacement thickness. So the rise in delta star is dominates over the rise in theta, and as a result the uh, shape factor also increases. So this is the reason why in the presence of adverse pressure gradient the value of shape factor goes up. Alright, so now we move on to the last question of today's session, that is question 9, which has also given us a velocity profile, a linear velocity profile, which is u over u infinity is equal to y over delta. We now have to find out the shape factor for this, which is we already saw, which is defined as the ratio of the displacement thickness delta star to the momentum thickness theta. Now is that value of shape factor equal to option A 5, option B 0.3, option C 3, or option D 0.5? Okay, so let's take a look at the solution. It's actually option C 3. So how do we get there? We simply have to find these two ratios and then take a, sorry, we have to find these two thicknesses, expression for the delta star and theta, and then we have to take the ratio. So starting with delta star, the momentum thickness, we saw how to compute it. So it's basically 1 minus u over u infinity integrated over y, going from 0 to delta. So this integration should be easier than the earlier one. since we have a simpler expression, which is y over delta, and integrating I get delta minus 1 by delta into delta squared by 2. So these cancel out, and 1 minus half I have delta by 2. This is the numerator, which is delta star. And then computing theta. So theta, the formula of theta is u over u infinity into 1 minus u over u infinity into dy. So basically this is the flux loss from going from a free stream velocity to a slowed down boundary layer, and this u over u infinity is the momentum loss. So if we multiply momentum into the mass flow rate, we get the momentum loss, right? So if we now compute, so going from 0 to delta, the first term is u over u infinity minus u over u infinity squared over dy. Now I'll replace them, 0 to delta. I have y over delta minus y over delta whole squared dy. Now we perform the integration, so I have 1 over delta, and this is delta squared by 2. This is 1 by delta squared into delta cube by 3. So if I take delta common, I will get half minus 1/3 into delta, and that's equal to 1 by 6 delta, so delta by 6. This is my expression of theta. So now if I compute the shape factor h, which is delta star by theta, delta we found out here to be equal to delta by 2, and theta we found out here to be equal to delta by 6. So if we now just take this ratio, we get 3. This is the value of the shape factor, and this matches with option C. So that's how we do it, and that's all. Thank you.